So once again, welcome everybody. My name's Jasmine and I work for WhatSpeed at the University of Waterloo. During the info session, if you have any technical difficulties, please feel free to reach out to my colleague Derek through the chat and he'll be able to assist you. Joining us today, we've got Elias Perunen today. So we're super excited to hear from him. Elias, welcome and thank you for joining us. Please note that there will be a Q&A section towards the end. So if you have any questions, please keep them ready and we'll get to them towards the end. So without further ado, I will turn it over to Elias now. Elias, please take it away.
Wonderful. Thank you so much, Jasmine. And thank you everybody for being here. Appreciate you taking time on your very busy Wednesday. This is a topic that is near and dear to my heart, Python versus R. And it's a question that keeps coming up is when you're getting into data science and trying to figure out what language should I learn? Should I learn Python? Should I learn R? What's the differences between the two? Which one's more relevant to the work that I'm doing? And what I'm going to try to do today is demonstrate how you can use both and that both should be looked at as tools in your data science toolkit. So that will be the focus of the session. I'll be demonstrating some of the strengths of each and some ways that you can actually use both of them together. So as mentioned, there will be the live QA section. So if you want to hold your questions to the end, you can do that. Or if you want to ask questions as we go, feel free to pop them in the chat. We'll be keeping an eye on the chat as we go here. So first off, let's talk about data-driven decision making. Boy, that's a vocal warm-up right there. So we're trying to get better than gut feeling when it comes to making better decisions in government, in the enterprise, in business world, wherever we are. But one of the biggest challenges has been we have just a ton of data, which may be structured or unstructured, might be across different databases, might be across different business units. How can we bring those together to get some value out of those data sets? And in 2021 study, about 3/4 of IT and business decision makers said that they expected to increase their investment in analytics. And whether that looks like software or the skills in order to query their data sets, it's clear that businesses across the world know the importance of the data that they have and that they may be missing out, on some critical insights. So Another really cool development that has happened over the last couple of years is we've seen analytic tools become not just more powerful, but easier to use. So it used to be a long time ago, you would need to have very specialized, expensive software in order to conduct any data analytics work on your data. Now you can go out and download a ton of free open source tools. For example, R and Python fit into this quite nicely. You can also move up to other analytics tools like Microsoft Excel, Power BI, and then once you get into the paid options like Tableau, you can do some powerful analytics without having to spend shed loads on specialized software packages. Another trend that's very clear is that figuring out how to monetize our data, the data that we're sitting on, is becoming important across all sectors of the business world. So our challenge is really a unique one. We have companies that are sitting on these gigantic data sets and they know we want to use these, we want to get some value out of these, either directly or indirectly, but maybe we're not sure how to do it. And the natural reaction might be, well, we need to have some data science experts that know how to use a language like R or Python to do this analytics work. And the question that a business owner may have is, well, which language should we be focusing on? Should we focus on R? Should we focus on Python? Or are they exclusive or are they inclusive? Can it be we can use them both at the same time? Here's what I found. As a computer science, with my computer science background, I've learned probably dozens of programming languages at this point in my career. Once you get the feel for one language, it becomes a lot easier to learn a second language and then a third and a fourth. And so what I find is most data science folks start out learning one language. for example, R or Python, and then they pivot to the complementary language. So what I've found in my consulting experience with the federal government, with Fortune 500s, is time and time again, a lot of the data science experts, they eventually end up learning both. And there's a very good reason for why that is. And just so I have an idea, maybe type in the chat, how many folks here have programmed with either R or Python or both or neither? Just before we get started and get into some of the demos and the comparison. So type in the chat, Python, R, both, or none. So I see some folks here with some experience with both, some with Python, a little limited use of R, both at an entry level. And we've also got some folks that, thank you. We got some folks that are saying that they have experience with neither. So both languages are net new to them. Where this discussion about which language should we use often comes up is once folks have either learned R or Python, the third language, the next language they tend to learn is a language called SQL, SQL, because that's the language that's used to communicate with large database products. And the question there is not an either or, do I learn R, do I learn SQL? You want to learn both because you can use both together. And it's the same thing with R and Python. So the background where R comes from, R has its roots in statistical analysis. It was built from the ground up to be amazing at doing statistical analysis. I'm talking about exploring data, doing regression analysis. It has a number of built-in functions that allow you to do statistical analysis. And when you need to go past that and get into more specialized statistical add-ons, especially when it comes to the natural sciences or physics or chemistry world, there are a number of specialized add-ons for the R language that are for, say, statistical analysis for chemistry. So very, very, very deep. R also gives you a lot of great data visualization tools, not just out of the box, but as part of the add-on libraries. So it's quite easy to make graphs that allow you to explore your data with just a line of code. That might take a little bit more work in Python. There are also add-on libraries for R. If you've worked with R, you might have heard of the Shiny library. And what Shiny allows you to do is take your R program and turn it into an interactive web page, almost like a data dashboard. There's also data, and it's got some great tools for doing some basic data exploration. On the other hand, Python has its roots in general purpose programming. It started out as a general purpose programming language. You can use it to write full applications on your computer. And it's the language that I learned before I learned R. As a computer science person, as a honors Bachelor of Computer Science at University of Waterloo, shout out to University of Waterloo, Python was one of the earlier languages that I learned, and then I scaffolded over to R later. And what I found Python has been fantastic at is when you need to get into more of the data manipulation and cleaning side, where you need to perform, say, you've got some data, some of it might be numbers, some of it might be text data, and you need to clean it up so it's in a consistent format. I find that Python's a bit easier to do those operations. Python has also developed a number of incredible machine learning libraries. So a lot of the development around machine learning, neural networks, actually in particular, if you have seen the AI service or the AI model called Stable Diffusion, if you're in the AI sector and you've been looking at artificial intelligence art, you might have heard of Stable Diffusion. There are a number, this is written mostly in Python. The models themselves are trained, and then you bring them into Python, and then you can run Stable Diffusion on your local computer to generate AI-generated images. So Python is fantastic at the machine learning and the deep learning AI side. with its roots in general purpose programming as well, Python is very well suited to tasks, for example, going out to a web page and scraping it, assuming that you're complying with the terms of service of that website. And of course, because it started as a general purpose language, Python tends to integrate a little easier with larger programs. But there's a lot of overlap between these two tools. And for some of the more basic use cases, you can use both to do data cleaning. For example, transforming text into numbers or creating calculated columns. Both are useful for doing data exploration. Both have libraries that allow you to do data visualization. Ours tends to be a bit easier to use, and there's a bit better documentation. Both can work with data across many different data types. For example, they both can work with SQL Server, Oracle SQL, MySQL, PostgreSQL, whatever database product you can think of, both languages can work with it. And finally, both are able to do some statistical analysis. They both have built-in tools for doing statistical analysis. So when it comes to more basic use cases, both languages can be somewhat equivalent. And in the first set of demos that we're going to do here, I'm actually going to show you the same project, just done in both languages. And we'll be able to compare and contrast and see the difference between R and Python and the different code or language that we have to speak to the computer in order to get it to do what we want it to do. And before I get to the demos, when I talk about programming languages, think of the programming language, whether it's R, whether it's Python, whether it's JavaScript, doesn't matter what the language is. Think of the language think of a programming language as the language that you use to ask your computer to do something for you. The only difference with a computer is that we have to be precise in the language that we provide to it. If we don't provide it in the exact way that it likes, for example, we're missing a bracket when we need one, or we put in some extra characters when they're not needed, we're likely to get something called a syntax error. And when we get a syntax error, that's the computer's way of saying, I don't know what you're asking me to do. Something doesn't look right here. I don't know what you're trying to get me to do. So we will get into the demos. I'll just pause for a second. If there's any questions so far, if you want to, feel free to put them in the chat. Otherwise, we're going to move straight into our demos. I want to make the most of our time here together. Let's talk about our first demonstration. We're going to do some basic data exploration with a sample data set. We're going to analyze a file. This contains smoking rates and lung cancer deaths for Canada. And we're going to produce a series of graphs to see if there seems to be any kind of a linear relationship between smoking rates and the lung cancer rate in Canada. And our data file that we'll be using for this project is a CSV, comma separated value text file. And it lists the smoking rates versus lung cancer deaths, and it's age adjusted. And this data is from the year 1990 to about 2011. And it is a composite of the following sources as shown on screen. So let's jump into R and get the programming party started. All right. So the software that we're using to run our code is called RStudio. And so I have a brand new R file ready to go here. And the first thing I'm going to need to do in order to read in my data file is I'm going to create a variable called data. And what a variable is it's just a name spot in memory where I can store some form of data. So for example, I'm going to be reading in this CSV file, think of it like an Excel file, from my computer into memory so that I can manipulate it. I can run a linear model. And I'm going to do read.csv, open brackets, because this is a function. So a function is something in R that does something for me. So read.csv, table 1, smoking versus cancer.csv. And as good practice, what I like to do is before I run any of my code, I'm going to save this as a new R file. So this is going to be demo1a live.r, and I'm going to save it in the same folder as my data files. And then I'm also in RStudio. I'm going to go to the session menu, hit set working directory to source file location. What that's going to do is instruct R that whenever you're looking for a data file, I want you to look in the same folder where this R file is stored. So now on my computer, I can press Control Enter to run this line of code. And now I have up in the top right here in my Variable Explorer, my data frame. So what has been read in is the CSV file. And if I click on it, it has been transformed into a table-like structure with columns and rows of data. So we go from 1990 to 2011. We have the smoking rate. We have smokers male, smokers female, and the age-adjusted lung cancer deaths over time. And so when I say a data frame, you can think of it like a table in memory that R is holding in memory. And so now I want to create that plot. I want to create those pairwise plots and see, is there a linear relationship between the smoking rates and lung cancer deaths? So I can use another function that is built into R called plot, P-L-O-T, open brackets, and I'm going to plot my data. When I press Control Enter, I get a new window that pops up. I'll bring this over. And here's our pairwise plots. So let's see here. I have my first column is year. My second column is smokers. And then my fifth row is my age-adjusted lung cancer deaths. So I can see here, it looks like we have somewhat of a linear relationship that as the smoking rate increases, the lung cancer death rate seems to increase. So this is interesting. As the smoking rate increases, the lung cancer rate seems to increase. So that suggests we may have a linear relationship. There might be something here. We'll have to run a regression model. So these are all the instructions I need in R to create plots of my data, to create the pairwise plots of my data to see, to do a quick exploration and see, do we have a linear relationship between our data sets? So I'm using the read.csv function from R, which instructs R to read in this CSV file from my hard disk into memory, store it in a place called data, and then I say plot that data into the pairwise plots. So far, 2 lines of code. That's all we need to do. This is all stuff that is built into R, by the way. Now we can build off of this demo. Now that we've seen that there seems to be a linear relationship between smokers and the lung cancer rate, we can now perform an ordinary least squares regression to see, is there a statistically significant relationship between smoking rates and lung cancer deaths in Canada. So we're going to use the same data that we just read in, and we're going to see if we're going to build a regression model and see if there is a statistically significant relationship. So let's jump back into RStudio. Believe it or not, we only need one more line of code to build our linear model. And I'm going to say model 1 equals LM, which is the linear model function. And we're going to be predicting our age-adjusted lung cancer deaths. I believe that's the column name. Yep, age-adjusted lung cancer deaths. We're going to predict that by the smokers. So our dependent variable is the age-adjusted lung cancer deaths, and our independent variable is smokers. What we're doing when we build up our regression model is we're running an experiment. And in our experiment, we have what's called a null hypothesis and a alternate hypothesis. And our null hypothesis, denoted by H0 or H0, depending where you are, is there is no relationship between smokers and the lung cancer rate. Our alternate hypothesis is there is a relationship between smokers and lung cancer rate. What we're going to be doing with our model is we're going to see, is there a statistically significant relationship? If it is statistically significant, we can reject our null hypothesis and say it appears that there is a relationship between smoking and lung cancer rates. And then we can look at the coefficients to figure out what is the size of that effect. And then we can build a model that tells us for X number of smokers, for X percentage of smokers, we expect to see this many lung cancer fatalities. So all we got to do is run this line of code. So age-adjusted lung cancer deaths, tilde smokers. I forgot to put in a comma and say linear model. I want you to use the following data set. I now have my model, and I'm going to print the summary of my model and see if we have a statistically significant relationship or not. So we take a look at our p greater than t value for the smokers variable. It is a very small number, 2 times 10 to the negative 8. So that's well under 5%. We'd be looking for 0.05 or better. These 3 stars tell us that we have our significance at well under the 0.1% level. So we can say that there's enough evidence for us to reject our null hypothesis. We would reject if we see about 5% or better. So we can reject our null, which says that there's no relationship, which tells us it appears that with this data, there appears to be a relationship between smoking and lung cancer rate. And if we take a look at the coefficients we get from our model, so our intercept, so that's where our line of best fit would intercept the x-axis, it would be around 26, or y-axis, excuse me, would be around 26.78744. Plus, and our coefficient for smokers would be 0.57941 x, where x is our smoking percentage, and y is our predicted lung cancer death rate. And in fact, we could do some really basic work here. We could say smoking rate is equal to, let's see here, let's use 30 as an example. And we will do, so we'll say predicted deaths equals 26.78744 plus 0.57941 times the smoking rate. So if we run that and then we print out predicted deaths, we get a predicted lung cancer deaths per 100,000 of 44.1. If we go back to our data frame and take a look at when we have a smoking rate of 30, our actual would be 43. So our model is under predicting a bit. So let's try with a smoking rate of 25. We get a value of 41.27269. So at 25, we're just about there. We're off by about we're off by about 2/10. If we try a smoking rate of 23, we get 40.11. If we go back to our data frame, we see for 23, well, we don't have a 23, but we see for 24 and 22, we have 40.48 and 40.05, and our predictor is 40.11. So we're probably right in, our model is quite predictive here. If we come back and take a look at the results as well, and we take a look at our adjusted R squared, 0.8581. So when we see a 0.8581, that tells us that our model fits the data quite well. So the amount of the distance between, say, each point of our data and the line of best fit that would run through all of them is quite small. So this model's predictive effect is quite good. And we're seeing that with plugging in all these different values for smoking rates and our predicted lung cancer rate. And again, if we plug in, say we plug in a smoking rate of 0, we would expect the predicted deaths to be 26.78744. So we're saying that even if there's no smokers, that there is a baseline level of lung cancer deaths that we are expecting. So this is just a very quick, basic overview of how to use R to do a bit of data exploration and how to run an OLS regression, linear regression using R. And we've done that in relatively few lines of code. That's the fun part about R and doing your data analysis. Because these plot functions are built in, because the linear model function is built in, you don't have to bring in a bunch of extra libraries and write a lot of extra code in order to do your analysis. You can just run your analysis right in R, read in your data, run your analysis, get your results. Which brings us over to the Python side. So I'm now going to show you the same thing. I'm going to do the exact same thing that we were doing in R, but we're going to do it in Python. This will give us two things. One, we'll be able to see how much more work it takes for us to do the same thing in Python. And two, we are going to be able to validate that we get the same results across both R and Python. So we'll be using the same data in our Python demo to explore if there's the relationship between smoking rates and lung cancer deaths. So we're going to build the same regression model. So now I'm going to flip over to the Spyder environment. This is the editor that we use in the DABI courses to run our Python code. So first thing I need to do, because the functions for running a linear regression model are not built into Python, I have to bring those in as bolt-on libraries. Same with reading in this data from my computer. So first thing I need to do is tell Python, I want to bring in the pandas library. And I'll say as PD. So I'm saying bring in the pandas library. And the pandas data manipulation library is what we use to read in data, to do data cleaning, to do data modification, exploration. This is the root package that we're going to be using for everything data related in Python. So first thing I'm going to do is I'm going to read in my smoking data, my CSV file, into a variable called data. You'll notice some similarities between R and Python already. So I'm going to say data equals pd.read CSV, table 1, smoking versus cancer.csv. And just for good measure, I'm going to save this file in the same folder as my data file. So this will be demo1 live.py. And if I run this program, in the top right here, I have my variable explorer. I've got a data frame. Again, that table, I've got columns and rows of data. If I double click on the data variable, I see, okay, I've got my years, I've got my smokers, smokers male, smoker female, and age-adjusted lung cancer deaths. You may also notice that in Python, in my Spyder editor, I have this highlighting. And what this highlighting is showing me is the minimum values and the maximum values in each of these columns. And it's also telling me that if I see these color highlights, that I'm dealing with numeric data. So that's not something that we get with RStudio. We have to do a bit more exploration of our data to find that out. But Spyder can give us a bit of details behind the scenes. So I'm just going to pause for a second and we'll flip. Let me see if I can show both Spyder and Python, or Spyder and RStudio side by side so we can see just how similar the syntax is for reading in our data files. So first thing we did in R, we did not have to bring in this import pandas because R has reading CSV built into it. In Python, we had to bring in pandas. That's our library that allows us to read CSV files or read data files. But creating a variable, for example, the data variable, was the exact same. We used the similar syntax across both languages. We use data equals, and then in R, we just do read.csv. In Python, we do pd.read_csv. So same, very similar code so far. So next, what I'll do is we're going to build our regression model. And the way that we do that is I have to bring in another library here. So I'm going to import the stats models.smf.formula.api as SMF. That way I don't have to type out statsmodels.formula.api every time I want to use the linear regression function. So I'm going to create model 1 equals smf.ols. And now I have to put my formula in quotes. So it'll be age adjusted lung cancer deaths tilde smokers. And then outside of the quotes, I put in a comma, and then I provide the data that I will use. And then I also have to say .fit so that the model gets generated. And I've got a typo here. It's not SLF, it's SM as in Michael F. So I now have my data frame and I have my linear regression model ready. And if I want to print out the results, I do print model1.summary. And here we go. I have my summary out. I have my output for this model. Let's take a look at how it looks. So we have an adjusted R squared of 0.858. If we flip back to RStudio for a second, we had an adjusted R squared of 0.858 there. Our regression coefficient intercept estimate was 26.7874. We have the same thing. So we have the same results across both R and Python. That's good news. So we see they're using approximately the same method to come up with their results. Our p greater than t is a very small number, which is being represented right now as 0 because it is 10 to the negative 8, which I don't know how small that is. Again, we have enough evidence to reject our null hypothesis. So we can say it looks like the smoking rate does have an impact on the age-adjusted lung cancer death rate. And again, if we take a look at these two pieces of code side by side, they're very similar. Just the way that we have to instruct Python how to build our regression formula is a little bit different than in R. But aside from that, they're very similar. We're able to use either R or Python to do the same thing. We'll move on to our second demonstration, which is trying to perform a quick data visualization to see if there's that linear relationship between the smoking rates and lung cancer deaths. So I will come back into Python here, and I have to bring in another library called Seaborn, which is a data visualization library for Python. I'm going to import Python or import Seaborn, and then I'm going to say seaborn.pairplot data. Oops. And let's see. And if I run this file now, I now get this awesome pairwise plot. I'm going to copy this image and paste it into Paint so that we can take a look at it together. So I've got years, smokers male, female, and age-adjusted lung cancer deaths along the columns. And same thing with year smokers. So if I look at age-adjusted lung cancer deaths and smokers in the lower left quadrant here, we see that we have a linear relationship. Again, just to reemphasize, we can do the same thing across both languages. We get the same results. Just the way we tell these languages to do our work is different. And you as a data science expert, you might feel that you're more comfortable in one language over the other. And if you're bilingual or trilingual, or you're one of those folks that's gifted and knows 15 different languages, you most likely have a primary language that you almost think in. For me, I'm like that with computer science and programming. I think in a language called C#, but I'm able to translate what I want to do into other languages. And it'll be the same thing here. But now let's talk about using them together, because I find that Python and R are tools. Just like a hammer and a screwdriver are both tools, they have applications in different contexts. Screwdrivers make poor hammers, and hammers make poor screwdrivers, but they can be used together to get a project done. And that's what we're going to demonstrate here. This demo is based off of some real-world consulting that I've done. So we use Python to do our data manipulation and data cleaning, which it's strong at. Clean up our data for use in R, and then we do our statistical analysis using R. So we're going to be using a fictitious data set. This is a data set I made up myself to determine if Which has the bigger impact on overall sales for a fictitious company? The number of stores they have or how much they spend on their ad budget? So this is fictitious. So if you're an ad or a marketing professional, please don't use this as a case study to go to your boss and say, hey, we need to increase the ad budget. So all fictitious. Let's start out in Python and we'll take a look at the data file. So I'm going to resize this. We're going to start a brand new data file. I'm going to save this as demo2a. And we will read in our data set. So first thing we're going to need to do is read in import pandas as PD, and then we'll read in our data file. And I'm going to clean up my variable explorer first so that we start from a very clean environment. So I have this data file. I read it in. It's a CSV file like before. And I've got 3 columns: sales, ad budget, and number of stores. Notice that only number of stores is highlighted. These 2 columns are not highlighted. Python has read these in because of the comma as text. So before we can use this in a regression, we need to convert these 2 columns over to numbers. As well, we have some very long column names: advertisement budget, number of stores. First thing I'm going to do is rename our columns. What I'm going to do is say data.columns equals, and I will give a list of new column names. If I run this code, you'll see my variable explorer updates. I now have 3 column names: sales, ad budget, number of stores. Now we are ready to do our data cleaning. I'm going to first clean the sales column. So I'm going to create a new variable called sales, and I'm going to set that equal to data square bracket sales. This gives me a copy of the sales figures column that I can now work on. So I'm going to say sales equals sales.str.replace. I want to replace commas with nothing. So just take the commas out of there completely. If I run this code, my sales column now no longer has any commas in it. My copy of that column. If I go back to my variable explorer, the original column still has those commas. So I'm only working on a copy right now. But now that the comma's out of there, I can convert this column to numbers. So I'll say sales equals pd.to numeric sales. This column is now a number. And so I can say data, the sales column in my data frame is equal to my cleaned sales figure data. So now I have cleaned that column. And we're going to do the exact same thing for our ad budget. So we've done the exact same thing on both the sales figures and our advertising budget. You can do this in R, by the way, but you have to bring in, but in this case, if you want to do the same data cleaning in R, you'd have to bring in extra libraries. So this is where Python has a bit of a strength over R. I brought in one library and I'm doing my data cleaning, my data manipulation. I can do calculated columns. I can do any number of data massaging operations right now. Now this is where we start to bridge over to R. I'm going to write this data frame, this clean data frame, out to a new CSV file. So I'm going to say data to CSV. I'll call this table2 cleaned.csv. I'll say index equals false because in Python, we get this extra column called index. If you take DABI2, spoiler alert, we cover what this index column does, when you may want to use it, and how you may want to change it. You have to take DABI2 if you want the full answer on that one. We don't need it at the moment, so we're going to tell Python, don't output the index column. We don't need that. So if we run this code and take a look inside of our folder, we now have this table2cleaned.csv file. Sales, ad budget, number of stores. Clean data file, ready for use in R. Time to go to RStudio. Going to fire up a brand new data file or brand new R file. We'll call this demo2 live. Here's what we're going to do. We're going to read in our cleaned data file. I'm going to clean up my variable explorer as well, give myself some room to work with. So I'm going to say data equals read.csv, table2 cleaned.csv. And here's that data. Here's that CSV file that I just made. It's cleaned. It's ready to go. Now we're going to run 3 models. Model 1 is going to be a linear model. And we're going to see the impact. We're going to see if we can predict sales by our ad budget using our data. And we print summary of model 1. We're going to set up a second model. We're going to predict our sales by our num stores. We'll see if there's any relationship between the number of stores and our sales and our predicted sales. And model 3, we're going to see which is significant when it comes to predicting sales. Our ad budget, our number of stores, or are both still significant? So notice what we're doing here. We are only doing a statistical analysis using R. We did all of our data cleaning operations in Python. So we read in our data, we build our first model, we run it, and we see that our ad budget is significant at it's well significant at the 5% level. Again, very small number, p greater than t value. So we reject our null hypothesis, which says that there's no relationship between our ad budget and sales. And we can say that as our ad budget goes up, our sales seem to go up. Woohoo! Let's go to model 2. We're predicting sales by number of stores. We print out that summary. Number of stores seems to be significant. So p greater than t, a very small number. So we can say that it appears that number of stores seems to predict as number of stores goes up, the sales are predicted to go up. Now we have a third test. We're going to control for both sales. We're going to control for both our ad budget and the number of stores that we have and see which one of these 2 variables, if any, is significant. So if we take a look at our new model, model 3, ad budget is still significant. So our p greater than t is still a very small number under 0.05. So it's significant at the 5% level, but number of stores is no longer significant. What this tells us is that in the presence of our ad budget is much better at explaining our sales figures rather than the number of stores that we have. It has the much larger effect on our sales figures. So the conclusion we may want to draw from this data, if we can replicate this across time, might be that as we increasing our ad budget is a more effective way to increase our sales. But of course, this is where the fun part starts. We have the result from our computer. Now it's up to us to interpret that result in the real world. What does this result mean in the context of our business? Does this mean that we just turn up the ad budget as high as it goes? Does this mean that we need to ignore the number of stores that we have? What does this result mean? And that's where your work as a data science expert really begins, is taking this result and interpreting it in context of the real world. And of course, we go into a lot of detail about not just the how to do this kind of statistical work, how to do this kind of analysis and building regression models and cleaning data in DABI, but then we go to the now what phase. Now what do we do with this? How do we interpret this in context of the real world? What do you need to keep in mind? What are the limitations of your models? What are some arguments you could make against or for the model? And then going even a step beyond that, how can you begin to not just say there's a correlation between this data, but how can we start to prove causation? Because that's really the ticket. We want to see, can we eventually prove causation somehow? But unfortunately, we only have a limited time together. I can't deliver all of DABI 1, 2, and 3 in one 40-minute session. And we do want to leave plenty of time for questions. So that's really where we get into the data analytics for behavioral insights, the DABI courses, of which I'm an instructor and founder of the DABI 2, where we go into a lot of detail with Python. But I think I will pause there and hand the controls back over to Jasmine, and we can start the live QA session. I don't know if you want to go into more detail about the DABI program.
Awesome. Thank you, Elias. That was very informative. So we have now come to the Q&A segment of the session. I would like to invite anybody, if you have any questions, please feel free to unmute yourselves now, and we can answer your questions for you.
So we just got a question through the chat Do you have any recommended resources for interpreting results? Yes, DABI2. I hate to, of course, as author of DABI2, I'm going to say, take DABI2. I might be a little bit biased, but truly, we do talk in the DABI courses, we do talk about here's how to start, here's the results you get. Here's what each of these different outputs means. For example, here's what adjusted R squared means. Here's what your coefficients mean. Here's all the different parts of a regression model and how they, and what they all mean. We go into all of those details in the 3 DABI courses. One resource you may want to try if you haven't in a while is you can actually go out to, if you need a bit of assistance understanding some of these concepts, you can also ask, this might be a little bit controversial, but you can also go to ChatGPT and ask ChatGPT about it. It has a fair amount of knowledge about statistical analysis, and it tends to be a pretty good resource for, say, if you're like me and it takes a while to, it took me a while to understand all of this stuff, but as a computer programmer first and a statistician second, I feel like I've been made an honorary statistician by working on these courses. But I would recommend DABI or asking ChatGPT. We've got lots of questions coming in. What factors should organizations consider when deciding whether to adopt Python or R as a data analysis tool? Are there any specific industries or use cases where one language is more commonly used than the other? My recommendation is to learn both. And the reason that I would learn both is because a lot of analytics, a lot of software now is integrating support for both languages. For example, in beta right now, you can write Python code in Excel to do your data analysis and create visualizations. Along with that, with Microsoft's Power BI, you can write R code to do the same thing. Both of these tools have their place. Commonly in my consulting practice, I see the data science teams that are responsible for massaging the raw data into something the statisticians and data experts can use. They'll use Python to do that. And then the data science experts, the statisticians, they will use R to conduct their analysis. I've seen that workflow many, many times. So I would recommend learning both R and Python. And it'll make it a lot easier for both of those teams to chat with each other too. Let's see. We have another question here. How much statistics experience do I need to be able to complete the course? Basic, intermediate, or advanced? Any recommended statistical knowledge or course to take before taking the courses? I believe the way that we've structured these courses is that the first of the 3 DABI courses, we go into those statistics. So we break down, what does all this mean? What is an OLS regression? What do all these variables mean? DABI2 is pretty much, you can think of DABI2 as we take what you learned in the first course, the basic statistical knowledge that you need, and show you how to use the computer to do all that work for you. And specifically, we do that using Python. So again, I would encourage you, check out DABI1, check out DABI2. DABI1 will, if it's been a while since you've taken statistics, or it's been a while since you've worked with OLS regressions, or you've never done it before and you're looking to get started with it, that's where DABI1 will be the most useful. And we assume no very limited prior knowledge or no prior knowledge. And in my course, the DABI2 Python for public data, we assume no prior programming knowledge.
Thank you, Elias. I will just mention very quickly, if somebody does want to refresh their Python skills specifically, we do have an Ed2Go course that I'll put the link for in the chat, and you can also enroll in that before the DABI course.
Wonderful. And I see that we've got the links here in the chat as well if you're looking for the different courses.
Yes. Elias, I do have some pre-submitted questions over here for you. Somebody would like to know, which software do you think will create better visuals to engage with stakeholders in the business setting?
I love this question. So which software makes better visuals to engage with stakeholders? It's both. What I find Python and R, they both can produce, you can make them produce visuals that look very similar to each other. But what we get into, and again, this is going to sound like a plug for DABI 2, but we do get into some details about some techniques around visual design, how to make slides, how to make graphics that explain your data's story. And we don't just show you the code in that course of how to produce graphs and pictures. We also go into, here are some principles of using shades, using colors, using font and iconography, using size, using base. It's almost like a graphic design 101 course for somebody with no graphic design experience. What I find is that both languages can produce compelling visuals if you put the time and the effort in to do it. I find that, again, they both give you kind of a blank canvas to work with, and then it's up to you to make the most of them. So I wouldn't say one language over the other is better at making those compelling visuals. The bigger principle to think about is, what is the story that you want to tell using those visuals? Is that visual easy to understand without having to explain it? Can it stand on its own? And again, we go into details about that design in the DABI 2 course. I think there was another pre-submitted question as well.
Sure. I can go ahead and read that out for you.
Sure.
I oversee a training and employment in tech program for survivors of gender-based violence. Which is more employable, R or Python?
My biased answer is going to be both. Either will make you very employable. Having R or Python will make you employable. Having both is going to increase your skill stack that much more and make you that much more employable. I would recommend try both languages, see which one speaks to you more, see which one makes, some folks are more comfortable with R, some folks are more comfortable with Python. The real key takeaway I want to leave everybody with today is not to think about R and Python as exclusive languages. They are both useful in different scenarios. They can both, for basic data analysis too, they can both do the same thing that we saw side by side, that we can write roughly the same code across both languages and get the same results. Knowing Python will help. Knowing both languages can only help you. So I'd recommend, if you haven't taken a dive into Python, you haven't taken a dive into R, pick one, get started. If it doesn't speak to you, pick the other, get started. See which one speaks to you a little bit more. And then we have a question here in the chat too. Would you be open to sharing what employment pathways would be available to participants after completing the DABI 1 course? I believe the DABI 1 course, we go into details about statistical analysis. We do touch on some R in that course, if memory serves me correct. So you would be well on your way to being able to do some basic statistical analysis after completing that DABI 1 course. So that's where you can start. So the pathways that you're going to open yourself up to is being able to build off of your knowledge of R, build off your knowledge of statistics, and start to continue down that data science path and continue down the analyst role. So lots of options.
Wonderful.
Great. And we got one other question here. Would causal econometrics be covered? We do cover that. I believe that some of that is covered in DABI 3. I would have to double check the exact coverage of that course though. And if I take the DABI certificate, I will learn both R and Python. We do R in the first course and Python in the second course. And then in the third course, I'd have to double check what we do. But you would be exposed to both languages, yes. And I think we'll wrap up with this question because we're getting a bit tight on time. What are the inherent limitations, if any, of R and Python when it comes to handling big data, parallel processing, and scalability in data science workflows? How do data scientists typically address these constraints through specialized tools or techniques? So we have to be careful when we define big data as well. One of my consulting clients, we have a database that when at full size, it's about 120 gigabytes plus or minus worth of data. If they are reading that entire data set into their workstation's memory, they do run out of memory. But the number of times that we actually need to pull all say 5 years of data points. And when I talk about data, I'm talking about we've got readings across 600 or 700 houses across at 5 to 15-minute intervals for 3 to 4 years. Like, we're dealing with a good amount of data. I also worked with a client where we had individual stock trades. This is a big Fortune 500. We had individual stock trades on a daily basis dating all the way back to the early 90s. These databases were massive. There was no way you could read them all into memory. But what we found was that we weren't interested in the entire data set all at once. We could read in chunks at a time and do our operations on those, do some data explorations on those, or do some summary statistics on the different chunks. When it comes to using R or Python, Python is generally a little better suited to dealing with large data sets, but getting those massaged maybe into smaller analyzable data sets that the folks in R will work with. But both languages are just as capable as each other of ingesting large data sets. It's all about knowing how much of the data do you actually need to bring in. And if you are getting into a scenario where you're exhausting memory, potentially splitting up your data set and doing analysis on different parts and then assembling a final story based on all of the data. So there are some other techniques that you could use to work with these large data sets. It's a little bit beyond the scope of DABI 1 and DABI 2, but Python and R are able to cope with large data sets. I've seen it in the real world.
Wonderful. Thank you, Elias. So with that, we have come to the end of our session. We want to say thank you to everybody for taking the time to join us today. And thank you to Elias for a wonderful session. Just a quick reminder that the first DABI course will begin on October 16th. I have the link in the chat. And if you have any questions, feel free to email us as well. Thank you so much, everybody. Have a wonderful day.
Thank you for joining us. Have a wonderful day, everybody.